Hello, everybody. Today we're going to be talking about the combined gas law. So, we've seen the three major individual gas laws. We know Boyle's law relates pressure to volume. They are inversely proportional, meaning when pressure goes up, that's because volume went down. We know Charles's law relates volume to temperature, and those are directly proportional, meaning that when temperature goes up, the volume will also go up. And lastly, Gay-Lussac's law, we know that when pressure goes up, that's because temperature also went up. So those are also directly proportional. So we've seen how these three different factors relate one at a time. However, you'll notice that there's some similarities between these equations. You'll see pressure in two of our three equations. You'll see volume in two of our three, and temperature in two of our three. Whenever you see pressure in Boyle's law and Gay-Lussac's law, that's always in the numerator. Same with volume, always in the numerator. And temperature is always in the denominator, or on the bottom of our fraction. And because of these relationships, we can actually relate all of them together or combine them into what we call the combined gas law. And that looks like all three of these sort of stuck together. It looks like this. We have P1 for our initial pressure times our initial volume divided by our initial temperature equals P2 times V2 over T2. So you'll notice it's just like Boyle's law, but with temperature underneath, like in these two, right? It has all three of these different gas laws combined into one, hence the name. So here is a fun little demo that I did. We're just going to watch it. And then we'll talk through what happened. Just a little background, this is just a soda can, a normal soda can. I filled it just a little bit with water, just a little bit, and then I'm gonna heat it up on the stove. That bowl on the left here, you'll see is just a bowl of water with some ice in it, so some really cold water. Okay, so again, what happened? I had a can, a little bit of water in there. I heated it up. You could see the steam coming out, right? You could tell that the gas was getting really hot really quickly because there's not much water in there, and metal is a very low specific heat capacity, so it heats up quickly. Then, once the air inside was really, really hot, we flipped it over and made it cool down really, really quickly and made it so no air could get in by putting it in the cold water with the sealed part underwater. So this is a demonstration of pretty much all the gas laws we've talked about coming together here. So which variable were we changing in going from the hot environment that we had on the stove to putting it in the cold water? What we were changing was the temperature, right? We're going from really hot to pretty cold, ice cold. So the temperature is changing and it is decreasing, right? Our initial temperature, our T1, is really hot because it's on the fire, and then it quickly goes to our new temperature, T2, when it cools down because we put it in ice water. So our temperature is going down very drastically and very quickly. So since the temperature goes down, right, these values or these ratios on the left and on the right need to be equal because that's what our gas laws have showed us so far. So if our temperature goes from big to small, or our denominator, what's on bottom, goes from big to small, then our numerator, or what's on top, would also need to go from big to small. So if temperature decreases, the pressure and the volume inside our can are also going to decrease. And so what's happening is the gas that's inside the can, it starts off really hot and the temperature goes down really quickly. So the pressure inside the can and the volume of the gas inside the can shrink. It gets really small. So there's very little pressure pushing on the inside of the can from the gas inside. Whereas there's what we call atmospheric pressure, which we're experiencing all the time, which is the gas molecules in the atmosphere running into us, right? The air that we're interacting with every day. So because the gas inside the can, the pressure and the volume go down very quickly, the pressure from outside, from the air molecules hitting the outside of the can, is much, much higher than the pressure pushing out from our can. And because of that, if there's a stronger force inwards than outwards, the can is going to be crushed, right? Which is exactly what happened. You can do this at home if you're safe and have some tongs with your parents. It's very simple, and it will work if you do it correctly every time. So, as far as using the combined gas law, again, you'll notice this looks very similar to the three gas laws that we have been working with. And so the three individual gas laws all assume that one variable is constant, meaning that one isn't changing, right? Boyle's law assumes that pressure and volume are changing, but temperature is staying the same, right? So we would have no temperature, and then that would be Boyle's law without the temperature, because the temperature's not changing. Same with, Gay-Lussac's assumes that volume's not changing, and then Charles's law assumes that pressure is not changing. So all three gas laws can actually be seen right here if you just cover one of the variables. So again, I can't do it here. I guess I could do it with my face. If you just take your hand and cover temperature, right? Then, look at that. Then we would have P1 times V1 equals P2 times V2, right? Which is just Boyle's law by itself. If you take your hand and cover both of the volumes, right? I can't do those because they're not next to each other. Then you'll just have Gay-Lussac's law. So if you don't want to memorize all four of these gas laws, and there's one more that we're going to be talking about next week, then you can just memorize this one. And if a problem doesn't tell you anything about temperature, for example, then just exclude the temperature, right? Because temperature is not changing, therefore just use P1 V1 equals P2 times V2. Or if it doesn't tell you anything about the volume, that means the volume staying the same, you can just memorize this and cross out or not use the volume terms, and then you have Gay-Lussac's law, but you just have to know the combined gas law in order to get there. So this way, if you figure out how to do this, right, just covering the one that's not changing, you don't have to memorize all four gas laws. You only have to memorize this one. So again, if a problem only mentions two types of variables, then you have two options. You can either go back and use the individual gas laws we've been covering for the last week, or you can just use this combined gas law for every single problem like this, and just ignore the variable that's not being mentioned. So again, if it says nothing about pressure, just ignore the pressure terms. Then you have V1 over T1 equals V2 over T2, which voila, is Charles's law right there. So I'll give you an example problem. Here we have a balloon, and it has an internal pressure of about 1.05 atmospheres, right? That's like the pressure that we're experiencing right now, a volume of 5 liters, so it's a pretty big balloon. If the temperature where the balloon is released, so we're going to let go of the balloon, it'll fly up, is 20 degrees Celsius, what will happen to the volume when the balloon rises to a new altitude? So it's going to fly up really high, where the pressure is lower, it's 0.65 atmospheres, and the temperature is also lower, it is negative 15 degrees Celsius. So here, right, we need to use the whole combined gas law because we're talking about pressure, volume, and temperature, all three of these. So we have our initial data, we have two parts of our final data. We need to know what will happen to the volume. So V2 is what we're going to be trying to find here. So just like in all the other problems we've done, you just need to define each variable, and I like to write them down. So if I look for P1, I like to start on the left, move to the right. P1, my initial pressure would be 1.05 atmospheres. It says right here, a toy balloon has an internal pressure of 1.05 atmospheres, and a volume of 5 liters. So that's going to be our V1 here, our volume at the beginning. Then if the temperature where the balloon was released is 20 degrees, so before we let the balloon go, the temperature, or our T1 initial temperature, is going to be 20 degrees Celsius. Again, that would be our T1. However, as I've hopefully drilled into you by now, we should use Kelvin as our temperature unit for all of these problems. So in order to do that, we just take our 20 degrees, add 273, and we get 293 Kelvin as our T1 value here. So now we have all of our initial data, our initial pressure, volume, and temperature. Now we can move on to the right-hand side of our equation and start finding those variables. So it says what would happen to the volume. So the volume is going to be, or V2, is going to be our variable, right? We don't know that, that's what we're going to try and find. When the balloon rises to an altitude where the pressure is 0.65. So the pressure decreased, our new pressure, our P2, will be 0.65 atmospheres, and the temperature also decreased. It would be negative 15 degrees Celsius. So our right-hand side of the equation, those variables would be P2, V2, and T2. And again, our T2, negative 15 degrees Celsius, needs to be converted to Kelvin, and negative 15 plus 273 gives us 258 Kelvin. So now we know all of our variables, except for the one that we're trying to find, and we can just plug them into our equation to give us something like this, right? Our P1 value goes in where P1 would be, V1, 5 liters goes in where V1 would be, so on and so forth. So again, V2 is our variable here, so we just need to use our algebra at this point and solve for that variable. So I'll walk you through it on the next slide here. So here, this is the exact same thing we had, just plugging in the values where they should be. How I personally like to solve these, again, there's many different ways, is if I have a bunch of numerical terms on one side, I'll just solve for that side first. That way there's fewer terms for me to deal with, right? So to get this number, I just did 1.05 times 5.0, all divided by 293, and that gave me 0.01792 as my value on the left-hand side. If we were using units, which ideally we would be, it would be atmospheres times liters divided by Kelvin would be our units here. Now, we need to get V2 by itself. So to do that, you need to get rid of these two terms, and you could do it a number of ways. But what I would do first is multiply both sides by my denominator here. So if I multiply both sides by 258 Kelvin, then these cancel on the right-hand side because I have one on the top, one on the bottom. And on the left-hand side, I have 0.01792 times 258 Kelvin. So if I solve that, I'll get 4.623. And on the right side, that will be equal to this same thing minus what was on bottom because that was canceled out, right? So I have 0.65 atmospheres times V2. So V2 is still not quite by itself. I have one more step, which is to get rid of this 0.65 atmospheres. To get rid of that, if I'm multiplying two things together, I would need to do the opposite and divide by the constant here, which is 0.65. So if I divide both sides by 0.65, these end up canceling on the right-hand side, and I end up with V2 equals 4.623 divided by 0.65. If I plug that into my calculator, I will get my final answer, which ends up being 7.11 liters. So that's it. It's just like we've been doing. However, there is one more variable we need to keep track of, right? So now we know all three individual gas laws as well as the combined gas law. In your homework, you're going to see that some of the problems require you to use all the variables like we just did in this example. Other ones will be similar to the problems we were doing with our individual gas laws. And like I said before, you're more than welcome to go back and look for the individual gas law, However, you don't have to. You can just use the combined gas law, and if there's no mention of one of the variables, say temperature, there's no mention of temperature, it only talks about pressure and volume, then just ignore the temperatures on both sides, and you'll have Boyle's law in that case, which is what you would need to use.